In this video, we're going to be looking at topic 9A, Kinetics, and this is part of the Unit 2 content for IAS Chemistry from Edexcel. So we're going to be looking at collision theory and using this to explain the effect of changing concentration, temperature, pressure, and surface area on a rate, understanding about what is meant by activation energy, how we can calculate a rate of reaction from a suitable graph, and also how we use Maxwell-Boltzmann distribution diagrams in order to show the effect of temperature on a rate. We'll also be looking at catalysts and how we can draw reaction profiles, as well as the use of catalysts in industry and how we show this on a Maxwell-Boltzmann distribution. So let's just go back over what you would have learned at IGCSE. The rate of a chemical reaction is determined by the change in a concentration of a reactant or a product per unit time. And it's very important with those last three words, the per unit time. A rate of reaction basically tells us how fast one of the reactants is used up and how fast one of the products is formed. And they are always to do with a change and a time. So an example of a unit could be moles per decimeter cubed per second, or centimeters cubed per second. And that's just about potentially what the concentration is changing as each second, or how much gas is being produced each second. And you may see diagrams that look like this to show you different graphs that show the rate of a reaction. Now, what you will tend to find is that the majority of the rates of reaction graphs are going to be a curve. And that's a problem when we want to try and use that information in order to determine the rate of a reaction. So what we should do is we should draw a tangent or a straight line to the curve, and that's what we see in this diagram here. So we want to determine the rate of reaction at point A. So what we do is we draw a tangent to the point A, and then we can determine 2 points that will lie on that tangent and use to determine the gradient of that line in order to determine what the rate of reaction is. So you can see on the diagram on the right hand side, your initial rate is the rate at 0. And then we can find the rate at any particular time. So if I want to find the rate of reaction at time t, I've drawn my tangent to the point at time t, and then I find out the gradient of that line, and that tells me the rate. When the reaction has stopped, you will see that the rate is 0, and then we get a straight line horizontally, so that's showing that our reaction is no longer happening. You should have seen all of this at GCSE, but if you can't remember, you might want to go back and have a look at that from your notes from year 11. So when we're talking about a rate of reaction, we are looking at something called collision theory. And collision theory states that in order for molecules to react, they must collide or hit each other. But a collision does not always guarantee that a reaction is going to occur. There are two factors that we must take into consideration. The molecules have to collide with a sufficient energy, and we call this the activation energy. And this is simply the minimum amount of energy needed for a successful collision. And when we say a successful collision, we mean the reactants hitting each other and then giving us our products. The molecules must also collide in the correct orientation. So they have to be aligned correctly in order for us to get a reaction happening. So if we look at these in a little bit more detail, the activation energy, as we've said, is the minimum energy that the particles have to have, and it is linked to the energy required to break the bonds at the start of a chemical reaction. So it can be linked to bond enthalpy. So that's how much energy does it take in order to break that bond, and that then allows the chemical reaction to start. And when we have a reaction profile diagram, like we can see here, we show our reactants and we show our products, and then the activation energy is the amount of energy it takes to get up to the top of this curve. And that's the amount of energy it takes for the reaction to get started. So this EA is the activation energy. When we're looking at orientation, what we must figure out is that what we must realize is that the molecules must meet in the correct direction. And remember, this is in 3D space. Although we would draw sometimes the molecules as flat molecules, remember they are three-dimensional. So an example of this would be when we're adding a hydrogen halide to an alkene, and you learned about this back in topic 5. If we have a reaction or the hydrogen halide approaching with the hydrogen towards the double bond, then we're going to get a possible reaction here. If, however, we have the bromine attacking or coming close to the double bond, we are not going to get a reaction. And if we have the hydrogen halide approaching from the side as opposed to from the bottom or the top, then again, we're not going to get any reaction. Now, you're unlikely to be asked too much about the actual orientation in terms of how does it attack and from where, but you need to be aware in an exam that you could be asked for the 2 factors for successful collisions. And you would simply say the activation energy and the orientation of the molecules. Now, there are 5 key factors that are going to affect the rate of a chemical reaction, and you have to be able to explain each of these factors using collision theory. So you will have met this in IGCSE. This is just taking it a step further and just making sure that we're using all the correct terminology and developing our answers to be a slightly more A-level type answer. So we're looking at the concentration, we're looking at surface area, the pressure of a gas, temperature, and a catalyst. So if we start off with looking at the effect of concentration, if we are increasing the concentration of a solution, what that actually means is that we have more particles in a specific volume. So you can see that in the diagram on the left-hand side at the bottom. A low concentration has few particles in that particular volume. For a higher concentration, we keep the same volume, but now we have more particles. And what this does is it causes more frequent successful collisions. The more particles you have in a specific area, the more likely they are going to collide with each other, the more often they are going to collide with each other, so therefore you get more frequent successful collisions. This is a key term. Whenever you are explaining a rate of reaction, you should be answering your question in terms of how we cause more frequent successful collisions. Those 4 words should always appear in your answers, and that ensures that you get the mark. You cannot simply just say successful collisions. You have to link it to the frequency, because remember, a rate of reaction is all to do with time. So if we look at the graph, we can see that we've got a graph that is not particularly steep. So this means that it's got a slow rate, because the steeper the graph, the faster the reaction. You'll have learned that back in GCSE. So what we see for A is we have a very, very fast rate, because the graph is much steeper and it levels off at a much quicker time. So we're going to get a fast rate or a slow rate, and we can show this on a graph. So that must mean that A is being completed at a higher concentration as opposed to B. So when we're looking at the effect of pressure, pressure is only going to affect a gaseous mixture. It cannot have an effect on solids or liquids, because changing the pressure of a solid or liquid is not going to change its volume, as its particles are already too close together. But changing a gas is making sure that you have more particles in a specific volume. So when we're talking about solids or liquids, we would refer to it as concentration. When we're talking about gases, we should be referring to it as pressure, but they're pretty much the same thing. So we have the same sort of explanation. So when we have more particles in that specific volume, we're going to get our key phrase again, more frequent successful collisions. And as I said, this is only going to be the case for a gas. If we look at the effects of surface area, the surface area of a solid is going to be the place where a reaction is going to take place. So a reaction cannot happen anywhere except the surface. So you can see in the diagram that when we have one big lump, all of these particles in the center are not taking part in your reaction because the reactions only happen at the surface of a solid. So the liquid or the gas particles that are reacting here cannot get to the particles in the middle of the solid. So if we increase the surface area, and we do this by decreasing the particle size, so that might be going from marble chips, for example, to a powder, that's going to allow for a more surface for the reactants to react, and you can see that in the diagram on the right hand side. So the same lump is now split into much smaller pieces, so there is more surface and there are a lot fewer particles hidden from those other reactants. So you'll find that this reaction happens faster because, again, we get more frequent successful collisions. Now, when we're talking about temperature, we look at it in a slightly different way, and this is where we introduce something brand new to A-level, and it is known as a Maxwell-Boltzmann curve. Now, this was determined by James Clerk Maxwell and verified by Ludwig Boltzmann back in the 1800s, and what this tells us is it tells us about the fraction of collisions that will have the required energy. So remember, we're all about this activation energy. So every molecule in a sample of a gas is going to have a very wide range of energy. And only a certain number of them are going to have a collision that has the required activation energy. So we have to actually look at the energy distribution of the particles in the sample. And it will look something like this. This is a Maxwell-Boltzmann curve. So we have the energy along the x-axis, and then on the y-axis, it's the fraction of molecules with a specific energy, or sometimes you might see the number of molecules. What they've basically done here is they will have been able to test if we think of it, if we imagine you could take the energy of every single particle and they put it into a bar graph like this. And then what they've done is they've simply drawn that curve over the top like that. So we take away the bars and we are simply left with the curve. So sometimes you might see it being referred to as a distribution curve. And we can use the Maxwell-Boltzmann curves in order to explain how how temperature affects it. So notice that neither curve is symmetrical. It is not like a bell curve where we have the normal and we have some symmetry. You will have lots of your particles being in the center, and then it will come close to the axis, but it'll approach it asymptotically, and that just means that it will approach the axis but never actually touch it. And the area under any two curves on the same graph are going to be the same because it's all to do with one set of particles. Now what we have here is we have different temperatures, and we have got T1 being a cooler temperature and T2 being a higher temperature. And what we can see that when we have a higher temperature, the curve displaces to the right. So the top of the curve, you can see, has moved to the right. That's telling you that more molecules have that specific energy. You will also see that the peak is lower, and that just means that the fraction of molecules is lower because we have a slightly wider distribution. Okay? And what we can then do is we can add on an activation energy to show what fraction of particles are going to have the required activation energy. So that's what this slide is just explaining, which is everything that I've just been saying. So they both start at the origin and approach the x-axis, but they don't actually touch. They are not symmetrical. The area under the two curves is the same. Peak T2 is going to be your hot temperature, and peak P1 is going to be your cold temperature or your cooler one. So T2 is displaced to the right and lower, and then we add on our activation energy and we look something like this. So if we say the activation energy is this particular energy value, what you can see with the blue curve is only the ones that I'm highlighting now, only that fraction of molecules is going to have the required activation energy. So this is the fraction of molecules with the activation energy. When we increase the temperature, what we see is that fraction becomes larger. So as well as the diagonal lined part, I also have the vertical lines that I've just drawn as well. So we have section 1, let's say is the bottom part, is for T1, whereas T2 will have section 1 and section 2. So your fraction that will react is going to be higher at a higher temperature. So if we then put that into our collision theory, increasing the temperature is going to increase the fraction of molecules that have the required activation energy. And because they're going to have this higher fraction of activation energy, this is again going to cause more frequent successful collisions, so we get a higher rate of reaction. It is very important that you are able to sketch, label, and explain the Maxwell-Boltzmann distribution curves. That is a very common exam question, and they will very commonly ask you to either sketch it or to label something on it. Now, when we're talking about a solution reaction, the collisions are slightly different to those in the gas phase. So in a solution, what you'll find is that the molecules are packed much more closely together, so the space is a lot less. Okay, as opposed to in a gas where they can be spread out amongst a very large volume. So what happens when the solute molecules get surrounded by the solvent? So your solid, remember, is your solute, and your solvent is your liquid. So you may have salt and water. When this happens in this surrounding, they are said to be trapped in what's known as a solvent cage. So in order for the reaction to actually happen, the solute molecules have to come into contact with each other by diffusion in the same solvent cage, and then that allows them to react. So for example, if I have solute A and solute B in a solution that I want to react, what you'll find is that they will form in a solvent cage. And that just means that the particles are completely surrounded by the solvent. So if I have a solvent cage that is only full of particle A, I'm not going to get any reaction actually happening. What I need is particle B to come into the same solvent cage, and now I can get my chemical reaction. So if they are not within that same cage, they will not react. So there's got to be some diffusion or movement of the solute molecules throughout the solvent. Then they come into the surrounding area of the solvent cage, and then they're trapped in there. And when that happens, they can then react. The last effect is looking at the effect of a catalyst. Now, we know that a catalyst is a substance that speeds up a chemical reaction, and it does this by providing an alternative pathway of a lower activation energy. I cannot stress enough that you do not say in an exam, it lowers the activation energy. You will lose marks. because a catalyst does not actually lower the activation energy of a reaction. What it does is it gives you another method in order to do that. And you'll learn more about catalysts in topic 17, where it tells you about the effect of how catalysts actually work, and you will also learn about it in topic 11. So what actually happens is we can explain the effect of a catalyst again using a Maxwell-Boltzmann distribution curve. Now this time for a catalyst, it should only contain one curve. A temperature explanation will contain two curves, but a catalyst will only contain one. What you will have though is you will have two activation energy lines. So what we see here is when we have no catalyst, only the blue fraction will react. So only the fraction of molecules that is coloured blue have the required activation energy in order to react. When we have a catalyst being added, what we're doing is we are moving that activation energy. So my activation energy is decreased. And then what happens with the catalyst now is the red and the blue fraction have the required activation energy in order to react. So again, we're increasing the the fraction of particles that have the required activation energy, so you get more successful collisions. You may also see this drawn on a reaction profile diagram. And all it does is we've got our reactants and our products, and we show that the curve for the activation energy with a catalyst is just smaller. Notice that they start and end at the same point. All that happens is this distance is shortened. So that with a catalyst, it might be quite a high activation energy, and with a catalyst, we just bring it down to a lower energy value. Now, some reactions can go through an intermediate, which are going to have a slightly different reaction profile. And what you can see here is they have two curves. And we will learn more about reactions that go through an intermediate in topic 11 of year 13. But basically, the point is the same, that when we have a catalyst, we're going to have this intermediate being formed, but you can see that the overall change in energy is going to be lower. The overall energy is going to be lower for the catalyst as opposed to the uncatalyzed reaction, because we are reducing that activation energy. Now, catalysts are regularly used in industry because they have major economic advantages. Lots of companies want to use catalysts because they were going to increase the rate of reaction. And so we're going to get more of our desired product in a specific time period. And because they're going to have this lower activation energy, your reactions can actually happen at a lower temperature. So you're going to get a decrease in your energy costs. So they are very economical. Now, the majority of catalysts that are used in industry are what we call heterogeneous catalysts, and that means that they are in a different phase to their reactants. And again, we will touch on catalysts in topic 11 and topic 17. So examples of heterogeneous catalysts are iron in the Haber process and vanadium 5 oxide in the contact process. And we can also get a catalyst being used in order to give a higher atom economy or a lower or higher percentage yield, because of course they are very useful to have as well. So let's finish off by looking at a past paper question. So this question is from June 2018, and we have hydromagnesite is a mineral containing magnesium carbonate. A student crushed some hydromagnesite and added a sample mass to excess dilute hydrochloric acid. This reaction gives off carbon dioxide and the gas was formed and collected. And the volume of gas was measured at regular intervals for 6 minutes, and we were able to draw this graph. So for 3 marks, we want to describe the changes in rate of reaction during the experiment and explain these changes in terms of collision. Now, most people will jump to simply describing what the graph shows. So the graph is steep at the start, not so steep in the middle, and then stops. Now that will still get you some marks, but it's not going to get you all of them because you've missed the second point. This is a describe and explain question. You have to be mentioning the number of collisions. So we're going to break this down into 3 points. So the first point is talking about the shape of the graph at the start. So what we find is that the maximum rate is at the start of the reaction. So you will always find that the rate of reaction is fastest at the start because you've got all of your all of your reactant particles available in order for them to react and collide with each other. As the reaction continues and as time goes on, what you find is the frequency of collisions decreases. Now, it's not enough to just say that it decreases, you need to explain why. And the reason that it decreases is because the reactants are being used up. So the more reactants that are reacting with each other to form the products, the less of them there are in order to continue reacting. So what you'll find is the faster the products are formed, the slower the reaction is going to get because you're running out of reactant particles. And then eventually, the rate is 0 and the reaction stops. And that happens at approximately 3.5 minutes. And that is because all the magnesium carbonate is used up. Be very aware that you cannot say that all of the reactants are used up because you have used excess hydrochloric acid. So you are not going to use all of that. You have to reference the limiting factor here, and that's the magnesium carbonate. So the rate is the fastest at the start. As the reaction continues, your frequency of collision decreases because you're using up your reactants. And eventually, once all the magnesium carbonate is used up at about 3.5 minutes, the reaction is going to stop. And there is your 3 marks. And you can see that there are the 3 points that we've just discussed. And the last question is from October 2018, and it is using the Maxwell-Boltzmann distribution curve. So we have ammonia being formed in the Haber process, and we want to explain, using this curve, why the addition of a catalyst increases the rate of reaction. Now, if they give you a diagram like this, the best thing that you can do is use it to your advantage. They're giving you the diagram for a reason. They want you to annotate or to label or to add something to it. So what we're going to do is we're going to add 2 lines. And the first line is going to be the activation energy with no catalyst. Then I'm going to add a second line, and I'm going to label that one the activation energy with a catalyst. Remembering that when you have a catalyst, your activation energy should be lowered, so the line will be to the left of the first line. That alone is going to get you 1 mark. You can say that a catalyst provides an alternative route with a lower activation energy, but you can simply just draw it on the diagram and you're saving yourself that time. The second mark comes from explaining what this means. And this refers to the fact that a higher fraction of molecules have the required activation energy to react. So we are showing on the diagram what is happening. Now, the second part is the explanation. So saying that we have a higher fraction of molecules that have the required activation energy or higher than the activation energy in order to react. And that's going to get you your second mark. Notice here that we are not referring to the number of collisions because it is only a 2-mark question and it is simply talking about using the distribution curve. And there's your mark scheme for that question as well. Now that's everything for topic 9A kinetics. Hopefully everything has made sense, and I would suggest that you practice some of these written answers using either past papers or through the A-level textbook. If there's anything you're not sure about, please feel free to leave a comment below, and we hope to see you back on the channel soon.